So I'm going to quickly go through this workshop and give you some ideas as to what possible answers would be fitting here. So the first question says glucose is mobilized for ATP generation in the muscle in response to epinephrine. So this is the beta-adrenergic receptor system. It says cyclic AMP phosphodiesterase is an enzyme that converts cyclic AMP to AMP. How would inhibitors of cyclic AMP phosphodiesterase affect glucose mobilization in the muscle? Well, the role of phosphodiesterase is to break cyclic AMP into AMP. Well, cyclic AMP, we know, hopefully you know this activates, wow, that's bad. Try that again. This activates cyclic AMP-dependent protein kinase, or protein kinase A. All right, and then protein kinase A begins to phosphorylate several proteins, and some of which lead to the activation of glucose transporters, which will allow glucose to enter the cell. So cyclic AMP, as long as it's around, there's going to be an impetus for glucose mobilization into the cell. Well, an inhibitor of cyclic AMP phosphodiesterase would prevent the breakdown of cyclic AMP, keeping its levels high, which would increase mobilization of glucose. So that would lead to an increase. That's what would happen if you added an inhibitor. Remember that cyclic AMP breakdown to AMP helps turn off the signal. It's one of the important parts of control of this pathway. A chelating agent is an agent that holds on to or binds to another, usually a metal. There's several metal chelating agents, and many of which are actually pretty effective at chelating calcium. So if we think about where we've talked the most about calcium, and there's a lot of areas, but in terms of the material covered in this class, we would have to say that this would impact, so this part would impact the phosphoinositide pathway. That's the one that has IP3. And if you remember, we start off with PIP2, right? And that's part of the phosphoinositide system, so the receptor is bound, and that activates the heterotrimeric G protein, which in turn turns on the alpha subunit when bound to GTP, turns on phospholipase C. So phospholipase C snips PIP2 into IP3 and diacylglyceride. The diacylglycerol, I should say, stays embedded in the membrane, and that can go on to further activate another kinase that's embedded in the membrane. IP3 can bind to a receptor that is in the sarcoplasmic reticulum, which is specialized endoplasmic reticulum that houses stores of calcium. And when IP3 binds to that receptor, that gated it's a ligand-gated transporter, it will allow the release of calcium into the cytosol, which then in turn can bind to calmodulin, which can then undergo conformational change, and the calcium calmodulin can then bind to other enzymes, kinases, etc., and begin the process of triggering a phosphorylation cascade in those cases. So if you were to add a calcium chelating agent, you would block the second messenger release. That once the calcium's released, you would just bind and sequester it so it could not go on and do what it would normally do if it were free in solution. What signal transduction pathways are impacted in a patient with diabetes? Well, one would immediately think of the insulin receptor pathway. It is quite possibly true then that a person with diabetes can't make insulin. Well, you wouldn't be able to trigger that pathway, thus mobilizing GLUT4, the glucose transporter. So that's one of the obvious transporter pathways that would be impacted with a person with diabetes. Now, some of the insulin receptors can also be linked to the MAP kinase pathway, which can lead to cell division, etc. But that can't be activated either if you're not getting binding to the insulin receptor. So I've always liked thinking about this. I've written whole tests based on superheroes and having people explain the biochemistry of the superhero. So really there's two things that happens when the Hulk transforms into the Hulk, when David Banner or Bruce Banner, depending on which part that you've seen, which series. If you saw the old TV series, they said David Banner. Bruce Banner shows up in the recent movies that you've been seeing with the Hulk. But two things happen. One is something triggers the Hulk's fight or flight response. He gets angry or frightened or threatened. And all of a sudden he gets a boost of adrenaline which kicks in his fight or flight response. And the other thing that happens, and probably if there were a radioactivity, maybe that somehow really connected this fight or flight response to the receptor tyrosine kinase pathways, which have to do with rapid cell growth, right? So the cells grow. Now, I don't know what actually causes the pants not to keep up with the growth. Somehow that the pants never rip. It's always a good thing. I prefer it that way, actually. But you ever notice that? That is kind of a puzzling thing. The shirt rips off, the shoes break out, but somehow the pants never do. Censorship? I don't know. Anyway, the point is these cell cycles are also linked to that fight or flight response. So something has to be impacting the really quick signaling of the receptor tyrosine kinase pathways to some degree, where the growth hormones and stuff are there. Now, what I can't explain would be how he shrinks back to normal size and reverses the process. So it's not a perfect thought on this, but it's fun to think about. I could have said, what pathways are triggered by being frightened or anger, and what could cause growth in the body? Well, that's not nearly as fun as thinking about the Hulk.